Hi, everyone. I am pleased to report that I think we are ready to do Polya's enumeration formula. So I'm very hopeful that by the end of this lecture, we will have in our hands a way to give a pattern inventory for our colorings under some kind of symmetric operation of a group. So we'll know how to compute the number of our colorings that not only are they not non-equivalent to each other, that will happen automatically, but we will know how many non-equivalent colorings there are with some number of each color somewhere. So, I mean, if I'm using 3 colors, I might want to know how many have 2 black, 3 white, and 4 red or something. I won't just want to know how many colorings there are. I'll want to know how many colorings there are of that type. And by how many colorings, I mean how many truly different colorings. That was the whole goal of Burnsides Theorem. Okay. And again, all of this is built on the back of Burnsides Theorem. Okay. And once again, I want to remind you that in this case, when we use Burnsides Theorem to give us the cycle index polynomial, all of that was, remember when we were developing the cycle index polynomial, we were assuming that every single vertex in a given cycle, had the same color, okay? Technically speaking, when we use the cycle index polynomial and just plug in the number of colors for each variable, we're no longer necessarily going to get the right answer if we have a special kind of coloring that we're considering, like in that example with the baton, bands that we were coloring where we wanted the consecutive bands to be different colors. Okay, so you have to be careful with this stuff. The Burnsides theorem itself works fine, but there you had to think about each individual permutation. Okay, so here we're just thinking about coloring, like any vertex can get any one of the colors. Any edge can get any one of the colors. Any face can get any one of the colors, whatever we're talking about, either vertices or edges or faces. Okay, so remember Burnsides theorem, that was the first big deal theorem in the stuff, was that the number of non-equivalent colorings n was equal to 1 over the size of the group operating on those colorings, okay, times the sum of permutations belonging to the group, psi of pi, right? And you know what psi of pi is, right? Let's concentrate on this though for a minute, okay? We're gonna really think about these terms right here, because it was really those values of psi of pi that motivated us to come up with the cycle index polynomial in the first place. Okay, so first of all, psi of pi is equal to the number of colorings. Okay, and by the way, when we think about the colorings that pi is operating on, a lot of those are equivalent to each other, right? That was the whole point of this whole exercise. Okay, so these things only become, or only kind of grouped together into non-distinguishable things once we kind of count all these things and then divide by the size of the group itself. Okay, so psi of pi is equal to the number of just wild, obnoxious colorings where I'm not paying attention to distinguishing things at all. It's just the number of colorings fixed by pi. Okay, and we knew that if I say, let's suppose that m is equal to the number of colors. Okay, m is the number of colors that we're going to be using. Okay, then this was going to be equal to, well, for every cycle that pi had, I can only choose one color. Okay, so basically I put a color on a cycle, And then in order for this thing to be fixed by psi, right, in order for pi to fix this thing, I would have to color every single other either vertex or edge or face that exact same color. So this is just going to be m raised to the number of pi orbits, okay, or number of pi cycles, if you will, okay? And so pi, that motivated us to kind of take pi and to associate with it, to take each one of these things and to associate with it a cycle index term, right? And so we would go like x1 to the a1, x2 to the a2, x3 to the a3, dot, 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 you know, xk to the ak, right? So we associate to every permutation a term like this, where there are A1 cycles of length 1, A2 cycles of length 2, etc., right? So let me just say A1 cycles of length 1, okay, A2 cycles of length 2, etc. Okay, so that's how we came up with this particular thing. All right. I promise all of this stuff is going to be useful for us very, very soon. Okay. So then, of course, we know that the number of colorings, so the number of colorings fixed by pi is equal to, let me write it this way, x1 to the a1 times x2 to the a2, dot, 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 xk to the ak, evaluated at, I'm kind of using some calc 2 notation here, okay? Evaluated at what? X1 equal x2 equal dot, 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 equal xk, and all of these are being put equal to m. So I get m to the a1, dot, 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 m to the ak, which is m to the a1 plus dot, 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 plus ak, right? A1 plus dot, 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 plus ak, that's just the number of cycles. The number of cycles, or orbits, if you want to call them orbits. Okay, so these little terms that we came up with in the cycle index polynomial were really, really helpful. Okay, and one more thing, let's go ahead and let n, right? So like m is the number of colors. Okay, we're gonna be concentrating on this correspondence between pi and its cycle index polynomial. But I also want to let n be equal to the size of the permutation. Right? Which is equal to the number of vertices or edges or faces being permuted, okay, in this whole coloring scheme. And we're permuting something, be it vertices or edges or faces. And what is n? What's the relationship between m, or between n and all of these powers on the various x sub i's? Well, n is going to be 1 times a1, okay, because those are all 1 cycles, yeah? So those only used up 1 element. Plus, okay, then I go to the 2 cycles, okay? Each one of those 2 cycles uses up 2 elements. Okay, so 2 elements for every of these 2 cycles. There are A2 total 2 cycles. Okay, plus 3A3 plus dot, 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 plus K, KAK. All right? So those are the things that we're gonna keep in our cognition here. Hopefully that's not too much to keep in your mind. But the whole point is we're concentrating on a singular element, yeah, a singular element in the sum like we're just concentrating on psi of pi once again, and we're really trying to understand what's happening with this thing, okay? So, just so you know where we're going and where we're headed, that is what we're working with here, okay? So n is given by this formula right here. So let us move on to bigger and better things here, okay? So again, what do we have? Let me just kind of write it here so that we can reference it. Pi corresponds to x1 to the a1, dot, 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 xk to the ak. Okay, so pi gives rise to that term in the cycle index polynomial. Okay. So for the sake of argument, let's just assume m, the number of colorings, is equal to 2, you know, for argument's sake. Okay. Let's just say B for black and W for white. Okay, so I'm coloring whatever it is I'm coloring, which is black and white. So here's the big question. Okay, and this is what we're going to really be concentrating on. Question, and I brought this up last time, but I looked at just a very basic version of this question. Now we're going to look at a much more in-depth, intense version of what it was I was starting to sketch out last time. But we're going to do it very slowly and very carefully so that we understand exactly what's going on. Okay, so here's the question. How many okay, of these pi fixed colorings have, okay, and I'm going to put a colon here because there's going to be several questions I'm going to ask. Have what? Well, what about 0 blacks? And okay, well, think about it for a minute. I only have 2 colorings. If I have 0 blacks, how many whites would I have to have? Remember, n is equal to 1 times a1 plus 2 times a2 plus dot, 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 plus k times ak. Right? So n is the total number of things that are getting moved around, okay? Total number of things that are moved around. So if I have 0 blacks, then they would all have to be white, okay? So it would be n whites. Okay, so what's the answer to that question? Well, the answer is 1. That's easy. You know what I'm saying? Okay, so the answer to that is 1. Okay, we'll revisit that in just a minute. But what about 1 Bs? And okay, if I have 1 black, how many whites would I have? Well, n minus 1. Okay, well, let's think carefully about that. Could I, okay, let's just think about it. Remember, we're thinking about the fact that we have, you know, A1 1 cycles and A2 2 cycles. Now, here's the thing. If I want to just have 1 black thing, could I possibly color anything in a 2 cycle black? The answer is no. If I color anything in a 2 cycle black, I'm automatically going to have to color another thing black. Yeah? So I can't color anything in a 2 cycle black. I can't color anything in a 3 cycle black. All I can color are things that are 1 cycles. That's it. I could color those black and that's it. And how many options do I have for which 1 cycle to color black? Well, A1. There are A1 options. And everything else is going to be colored white. Okay? So the answer to this is A1. Okay? And let me just remark here that so A1, let me just say that no 2 cycle 3 cycle, etc., can have a black element. Okay. I wouldn't be able to color a vertex in a 2-cycle black because it would require that I color everything else or the other thing in that 2-cycle black. Similarly for larger ordered cycles, I can only color a one cycle black. Yeah. Okay. So at this moment, well, actually, no, let's go one step further. All right. So I'm going to give myself a little bit of room here. Okay. What about 2 blacks and n minus 2 whites? Okay. Well, that's a little bit more interesting. Okay. Okay. So first of all, this guy right here, that guy right there came exclusively from the 1 cycles. Okay, that came exclusively from the 1 cycles. Okay, I couldn't use the 2s, the 3s, or anything beyond that. Okay, but let's think about this. If I want 2 blacks, well, there's a couple of ways that I can do that. I can either do it with the 1 cycles, or I can do it with the 2 cycles. Okay, but I can't use the 3 cycles. Because any 3 cycle, if I color something black in a 3 cycle, I'm going to get 3 black things. And that's not going to work. You know what I'm saying? Okay. So what's the deal here? Either I have to color 2 1 cycles black and everything else white. I have to color 2 1 cycles black and everything else white. How many ways can I do that? Well, A1 choose 2. Okay, that's if I decide to color 2 1 cycles black and then everything else white, or, which means plus, or I can choose a 2 cycle to color black. I can choose a 2 cycle to color black, and then everything else would have to be white. So how many ways are there for me to choose a 2 color or a 2 cycle to color black? Okay, because that would use up 2 blacks, right? Well, the answer to that is A2. Okay, so what is the deal with this? Let me just kind of mark this off here. This guy right here is coming from the 1 cycles. Okay, and this second summand right here is coming from the 2 cycles. Okay. Now at this moment, I want to back up and look at these carefully. Okay, because there is something deeper going on. Okay, one, okay, I don't, I'm just going to write what it's equal to. It's actually equal to A1 choose 0, because I can't choose any 1 cycles. Right, if I want 0 blacks, I can't choose any 1 cycles to be black. Okay. This is going to be, so A2 choose 0, I can't choose any 2 cycles, etc. AK choose 0, I can't choose any of the K cycles either. That's really what's going on with this 1. This 1 is really just a product of a bunch of binomial coefficients. Okay, what about A1? Okay, what's A1 really equal to? Well, what's going on here is really, I said, well, I could choose 1 of the 1 cycles, but I can't choose any of the 2 cycles. I can't choose any of the 3 cycles, etc. I can't choose any of the K cycles. Okay, so there's that. What about this guy? What's this really equal to? Okay, well, what this is saying is there are 2 cases, the 1 cycle case and the 2 cycle case. Okay, so what's the deal with this? Either I choose 2 1 cycles and then, and then nothing from the other cycles. Okay, so A2 choose 0, ... AK, choose 0. Or, okay, Or I choose a 2 cycle and nothing from any of the other cycle types. Okay, so I choose no 1 cycles to color black. All of those are going to be white. And I choose 1 of the 2 cycles and then none of the 3 cycles. Of course, anything beyond 2 is out automatically anyways, because I can't be coloring, you know, a 3 cycle. Once again, if I color 1, I'm going to have to color 3 black. Okay, so dot 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 a k choose 0. Okay. You see what's happening here? See a little pattern starting to emerge? It looks like it's a sum of a product of a bunch of binomial coefficients. Ooh, okay, so let's think about this for a minute. Okay, let's go 1 step further, and then I think we'll be ready to write down a formula. What about 3 blacks? And don't forget what n is. Okay, n is just the total number of things that I'm permuting around. Okay, what about 3 blacks and n minus 3 whites? All right, well, let's think about that carefully. Okay, that's a little bit more interesting. 3 cases. I can either take all of my black elements from, I can take all of my black elements from the 1 cycles. Okay, so I'm just going to straight up write it down. I can take all of my blacks from the 1 cycles, and that means I can't take any, or everything else is going to be, once I have my 3 1 cycles to color black, everything else is white. Okay, so A2 choose 0, dot dot dot, AK choose 0, or, all right, so this guy right here, what's this coming from? You know, I'm going to put some green in here, I guess. That's the all 1 cycles. That's the all 1 cycles situation. Okay, or what else? Well, I could take a 1 cycle and could I take anything beyond a 2? If I took a 1 cycle and colored it black, I took something beyond a 2 cycle, like a 3 cycle, that'd be too much. I would have 4 blacks at least, okay, and that's not good. So I could take 1 cycle, and if I don't want to like repeat the situation I was already in, could I ever take 2 1 cycles? No. If I took 2 1 cycles, what would happen? Well, if I took 2 1 cycles, exactly 2 1 cycles, then I would have to take 2 cycle at least, which would give me at least 4 blacks again, which is no good. Okay, so A1 choose 1, take 1 1 cycle, and then I'm going to take a 2 cycle. That's the only option I have. So it's going to be A2 choose 1, right? Choose one of the 2 cycles to color black. Okay, then it's going to be A3 choose 0, dot dot dot, AK choose 0. But in this situation, okay, so here we go. This right here, this summand arises from a 1 cycle and a 2 cycle situation, okay? But in this case, I actually have one more situation I have to think about. Namely, I want 3 blacks. Well, one way that can happen is if I take everything, or if I take a 3 cycle and just color everything in that 3 cycle black. Okay, so basically I don't take a 1 cycle, I don't take a 2 cycle, I do take a 3 cycle, I don't take a 4 cycle, dot dot dot, and I don't take any of the other things. Okay, so what's going on here? This is the 3 cycle situation. Okay, that's the 3 cycle situation. Interesting. Interesting. What is going on here? Okay, it looks like I have a sum of products. I have a sum of products of binomial coefficients. A sum of products of binomial coefficients. Is there any way that we can make sense of what's going on here? Okay, let's go to the next page here and let's try to do it. Okay. Okay, so, Here's a little note for us, okay? So here, watch this. Note the following. Okay, note. What would happen if I were to take b plus w and raise it to the a1? I kind of hinted at this last time. Okay, but then I multiplied this. Now the thing is, if I went back to this previous page right here, okay, if I go back to this previous page, I see, in the first summand, I see 3 and a bunch of zeros. But then in the second summand, I see like a 1 and a 1 and a bunch of zeros. Like 1 plus 1 is 2, whereas 3 plus a bunch of zeros is 3. Whereas in the third summand, I see a 1 on the 3 thing, and then I have a bunch of zeros. So like the third summand, the numbers I'm choosing add up to 1. Second summand, the numbers I'm choosing add up to 2. The first summand, the numbers I'm choosing add up to 3. What is happening? What is going on? Well, it turns out it has to do with the fact that 1 times 3 is 3. It's kind of like what was going on in the cycle index polynomial. Notice that I have a 1, 1, 1, and I have a 1 type 1, 2. Do you see this? So this is like, the cycle type times 3, that's 3. Yeah? What's going on here? The cycle type times 1 plus the cycle type times 1. Hey, that's 3. That's what's consistently happening here. Notice that the same thing happens over here. The cycle type times 1 is equal to 3, right? You have this consistency going on here with 3s all around. 3, 3, 3 every single time, okay? So how in the world could I how in the world could I capture that over here? Well, that's what we're going to do here. We're going to say, well, I can like imagine, like this is like to the first power right here, right? And this W is to the first power, okay? And when I expand this thing, the powers of B are just going to be increasing by 1 at a time, and the powers of W are going to basically be decreasing by 1 every time, okay? How could I get this kind of, this situation where when I expand it, I'm not jumping by 1s, but by 2s? Well, the way you accomplish that is like this. Instead of B plus W, I'm going to do B squared plus W squared, A2. And then when I expand this out, you're going to get a bunch of 2s multiplied by these A2s. Okay, and that's helpful because like if I do A2 choose 1, I'm going to have a B squared right there. And that power on B, which is 2, is the same thing as 2 times 1. Okay, so this thing is trying to capture what we were noticing over there. So what am I going to do with the next one? Well, let's try B cubed plus W cubed, A3. Okay, and then, B to the K plus W to the K. Let's raise that. Let's raise that to the AK. All right. So watch this. Okay. What is this equal to? Well, first of all, that ought to remind you of the cycle index polynomial. Okay. First of all, let me just kind of back up here for a minute. Notice that this right here, this giant product, that's just x1 to the a1 times x2 to the a2 times all the way up to xk to the ak simply evaluated at what? X1, what have I replaced X1 with? Well, B to the first plus W to the first. What have I replaced X2 with? Well, B to the second plus W to the second. Dot, dot, dot. I've replaced XK with B to the K plus W to the K. So that whole thing is really just that cycle index term that corresponds to our permutation. All I've done is I've replaced the x's with, like x sub I, with b to the I plus w to the I. Now watch what happens here, okay? Watch what happens here when I expand this. So the binomial theorem says that that first thing is what? Well, it's A1 choose 0, W to the A1, actually here, I'm gonna, oops, come on. I'm actually gonna put the B's in here just for completeness sake. So B to, come on. What is going on with this thing? Okay, come on. B to the 0. Sorry guys, here, I'm gonna have to take a minute to fix this, just a second. Sorry about that. My pen was in utter rebellion against me and I had to kind of go out of the program and come back in. Okay, so it's gonna be, I'm just expanding the first factor here, B1, B to the first plus W to the first raised to the A1. So it's gonna be A1 choose 0, B to the 0, W to the A1, okay? Plus A1 choose 1, B to the 1, W to the A1 minus 1, plus dot, 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 plus, okay, what's the last one going to be? A1 choose A1, B to the A1, W to the 0, right? You know how this works, okay? Times, okay, times what? Now let's expand the second one, and this is where the magic starts to happen, okay? So let's see here. It's going to be A2 choose 0, B to the 0, W, right? So like the choosing, or I want to think of that as choosing the number of blacks, okay? So it's going to be B to the 0, and what's it going to be? W, think about it now. It's actually, instead of just W to the A2, it's W squared to the A2, which is W to the 2A2. Okay, plus, what's the next one going to be? A2 choose 1. Okay, now what's being raised to the first power? It's not just B, it's B squared. Okay, so it's going to be B squared W to the 2A2 minus 2. Okay. Okay. The total power needs to be 2A2 every single time. Okay. Plus dot, 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 plus A2 choose A2. It's going to be B to the 2A2, W to the 0. Okay. And I'll write one more term here just so that we can see all of it play out. So this is A3 choose 0, B to the 0, W to the, now we're talking about things being raised to cubes. So this will be W to the 3A3 plus A3 choose 1, B cubed, W to the 3A3 minus, right? Because that means from one of those factors I took B cubed, so I lost 3 W's. So it's minus 3 plus dot, 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 plus A3 choose 3, or A3 choose A3. And it's going to be B to the what? Well, to the 3A3, W to the 0, those parentheses, plus, etc. Or not plus, times, etc. Right? So times, etc. Okay? And notice what happens here if I expand this out. What happens if I expand this out? And this is where all of the glory happens? So if I were to expand out this huge product, what happens? Okay, this is equal to, well, let's kind of think about this. Look, if I take all the zero terms from each one of these factors, if I take all the zero terms, what am I going to get? Well, it'll be A1 choose 0, A2 choose 0, ... AK choose 0. Okay, and I would have W to the A1 plus 2A2 plus 3A3 plus ... plus, right? All of those W powers would get added together. K, AK. But what's that? Do you remember? What's A1 plus 2A2 plus 3A3? That's just N, right? Remember, N was equal to that. If you go back to, oh man, it's going to make me scroll through all of these things again. Okay, if you go back here, remember N was equal to that sum. N was the total number of things that we were permuting, be it vertices, edges, or faces, what have you. Okay, so that's just N. Okay, so let me at least mark that in yellow so that we know that that is N. Okay. Okay, what's the next summand going to be? Well, okay. What if I just want b to the first power? Okay, so plus something times b to the first power. Well, clearly I can't take anything from the second factor onward. Is that starting to sound familiar? Can't take anything from the second factor onward. Remember before we were talking about I can't take any 2 cycles onward, okay? So if I want a b to the first power, I'm gonna have to get it from the first factor, right? So this is gonna be A1 choose 1, and then I have to take a bunch of zeros from everywhere else. A2 choose 0, all the way up to AK choose 0. This would be b to the first, okay? And what's W going to be? Well, I just lost 1, right? Because look, I lost 1 because what I did is I took this factor right here, or this summand. I took that summand from that factor. Okay, I lost 1 from A1, and well, subtracting 1 from the previous power is just n minus 1. So this is W to the n minus 1. Okay, what's next? What's next? Well, now I want to know what is going to be sitting next to, I ask you, what's going to be sitting next to b squared W to the, now I think you get the idea. If I take b squared, that's essentially going to subtract 2 from the total power on W. So it's to the n minus 2. Okay, how could I build that? Well, you know, I could take my 2 b's from the first factor, the third summand, and that would be A1 choose 2. Okay, A1 choose 2, and then I would have to take zeros from everywhere else. Okay, plus, I'm going to actually move this thing over a little bit just so I have a little bit of room here. Plus what? Well, if I want to have 2 things, can I take 1 from the first factor at all? Could I do that? No, because the lowest power of b in any of the other factors is 2. And so that would give me something that was too large. Okay, so the only other thing I could do here would be to go A1 choose 0, A2 choose 1, A3 choose 0. Okay, A3 choose 0, ... AK choose 0. Okay, this thing. And what is the power on b and W here? Well, this is b squared W to the n minus 2. Okay. And I think that you see what's going on here. I think, okay, because if you go back to the previous slide and you look at what we were doing over here, These are exactly the formulas we were getting for the number of pi fixed colorings of a specific type. And specifically what we just got was, these guys right here. We were about to get the 3Bs and n-3Ws, but we flat out got those formulas right there, okay? So what have we noticed? What have we noticed here? So this is amazing. So plus ... right? Therefore, okay, and this is kind of the big punchline here. Let's kind of write this on the next page, right? So we see, and this is, we flat out have proved it. So we see that the number of pi fixed colorings, okay, colorings with I blacks and n-I whites is equal to, I mean, we were getting the counts as the coefficients of that funny generating function we just came up with, okay? So this is the multivariable generating function. This is the coefficient, right? We have this nice notation we've come up with. The book's presentation, they kind of do, they basically do an example, which is sort of nice, but it doesn't really penetrate to the depth of what is actually going on here. And that's what we're doing right now, okay? So it's equal to the coefficient of b to the I, w to the n-I of this, b plus w to the a1, b plus w, or b squared plus w squared to the a2, and here I'll put b to the 1 just so it's very clear what's happening, all the way up through b to the k plus w to the k, a sub k. Okay, which by the way is equal to b to the I, w to the n-I, that coefficient of the cycle index polynomial term that corresponded to pi, x1 to the a1, x2 to the a2, ... xk to the ak, but I was evaluating this thing at x1 equals b to the 1 plus w to the 1, x2 equals b squared plus w squared, ... xk equals b to the k plus w to the k. All right, so that's amazing, okay? That is an amazing thing for sure, that I can actually get a handle on the number of pi fixed colorings with exactly IBs and n-IWs by just taking the cycle index polynomial and then plugging in b to the first, or plugging in for xi, b to the I plus w, or b to the j plus w to the j for all of them, and then extracting the coefficient of b to the I, w to the n-I. And that will automatically be the number of colorings fixed by pi of a particular type of that inventory. And one thing that I would note is, like, if I take b equal to w equal to 1, for instance, I'm just going to get the, like, if I take b equal to w equal to 1, so note, here I'm just going to make this little note right here. So note, if we take b equal to w equal to 1, you know, what are we going to get here? You know, we're going to destroy the you know, we're not going to be able to tell like where b and w are anymore, but we're just going to end up getting, just get the total number of pi fixed colorings again from this you know, BW generating function. Right? Because think about it. If I plug in, you know, if I put one here, right? If I put one here and I put one here and I put one here and I put one here, etc. I put one here and I put one here. What am I going to get? I'm going to get 2 to the A1 times 2 to the A2 times 2 to the AK. And overall, it's just going to be 2 to the total number of cycles, was exactly the number of pi fixed colorings again. Okay, pi fixed colorings again from this BW generating function. So I can still recover the information I had before. I still haven't lost anything. I can still get it back by simply taking B equal to W equal to 1. But I've kind of introduced these new variables so that I could refine our count and actually extract the number of colorings of particular types here. Okay, so that is kind of the key, right? And by the way, and here's just a little remark, and then I'm going to go over into our notes and we're going to look at the Polya enumeration formula theorem. So here's a little remark. You know, if 3 colors, you know, red, green, and blue, then replace xj with what? R to the j plus g to the j plus b to the j. And I'm telling you, the same exact argument is going to work as what we just did now, except we use the binomial theorem. Here you would have 3 things raised to a power. You would have to use the multinomial theorem, which we know, okay? But it's still going to work. Same exact argument's going to work. You're still going to know that if you extract a particular coefficient, it's going to count the number of pi fixed colorings for this term. And because Burnsides theorem adds all of those cycle index polynomial things together, total, like, you know, each one of those summands counts the number of colorings of a certain type. Each one of the summands counts, you know, the number of colorings that have I, B's in it. Well, if I count all those for every one of those summands, then all it's going to do, the Burnside theorem cycle index polynomial, is going to literally count all the colorings, not just the ones that correspond to pi, all the colorings that happen to have a certain number of black vertices and white vertices, etc. Okay, so that's the beauty of what's happening here. So I want to go over here and look at the actual statement of the Polya enumeration formula, and then maybe we'll do an example and we'll finish this off. Okay, here we are over in the notes here, and here is the Polya enumeration formula, stated in all of its lofty glory here. Polya enumeration formula. It says, let S be a set of elements, you know, that have been colored in some meaningful way, right? G be a group of permutations of S that acts to induce an equivalence relation on the colorings of S. Okay, so the inventory of non-equivalent colorings of S using 2 colorings is given by the bivariate generating function. This is exactly what we were kind of arguing for on the other page. This right here is what you've replaced x1 with. E squared plus w squared, that's what you've replaced x2 with. Dot, dot, dot. This right here is what you've replaced xk with. Okay. The inventory using M colors, and then you just kind of, you know, there you know, so because you're kind of running out of letters, you just say color 1, color 2, etc. And essentially what you've done is you've replaced x1 with c1 plus c2, etc. And then x2 you replace with c1 squared plus c2 squared, etc. Okay, dot, dot, dot. And then this guy right here, this is what you've replaced xk with. This is going to do all of the dirty work automatically of actually generating a pattern inventory for your colorings. And again, you can get, right, you get the total number of colorings, get number of colorings by putting, you know, C1 equal to C2 equal to dot, dot, dot equal to Cm equal to 1, right? And equivalently, look, you know that what's happening there, if you put all of those equal to 1, that's just like putting x1 equal to dot, dot, dot equal to x, what is it, xk equal to m, right? Because each of those is a sum of m1s if I replace all those colors with just 1, okay? So once again, I haven't lost any information that I had before. I actually have more information, okay? So that's the Polya enumeration formula. And the proof, we really just did it. We only concentrated on 2 colors and one term only in the Burnside formula. One term in the cycle index polynomial that arose from a single permutation. Then when you think about it, you say, well, yeah, but adding all those together is just simply going to add them all up. And then the division by G, the size of G at the end, all that's doing is just simply getting rid of all the copies of things, right? And it's counting only truly distinct colorings, right? That was the magic of Burnsides theorem. Okay, so let's kind of look at an example to finish our time here together, okay? So we're gonna 5-color the vertices of the icosahedron, okay, which is one of the things that we looked at. Now, X4 didn't appear in the icosahedron. That was the cycle index polynomial that we came up with, okay, at great laborious effort on our part, okay? So if I wanted the number of 5 colorings, I could obviously just plug in all of those variables equal to 5. And as you can see, I would get, you know, the x1 squared, x5 squared, right? So that's 2 1 cycles and 2 5 cycles. And again, this was operating on vertices of the icosahedron. So there were 12 elements total that were being operated on there. You can see that if I plug in 5, I'm going to get 5 to the 12th. I'm going to get 5 to the 4th in both the second and the 4th summand, right? So that's why you have 24 plus 20 is 44 times 5 to the 4th. Okay? And then you have 15 times 5 to the 6th. And then you have to divide by the size of the group. And you get about 244.5 million distinct 5 colorings of the vertices of the icosahedron, which is amazing all by itself. But look, our theorem says if I wanted to actually know not just the total number of colorings, but even colorings of a particular type, what I would do is I would straight plug this thing in to, I would straight plug this thing in, like I would plug in x1 equal to this. I'm using white, black, red, green, yellow. White, black, red, green, yellow, okay? I'm plugging that in for x1. I'm plugging in white squared plus black squared plus red squared plus green squared plus w squared for x2. Okay? And I'm just straight gonna plug this in. We're gonna expand it out, and that is going to be what happens here. Now, you know, I do have a little maple thing that I could do this with, but I'm actually going to go over in another file and show you, or actually I'm going to go over into Wolfram Alpha and show you that you can actually expand this thing out even in Wolfram Alpha, okay? And it will pull it off for you automatically, okay? All right, so I'm going to go over and do that, and then we're going to call it a day. All right, so I'll be right back. All right, here we are over in good old Wolfram Alpha. I have typed everything in here, and I'm going to ask Wolfram Alpha to expand this thing, right? Remember we had x1 to the 12th. We replaced x1 with the sum of the color variables raised to the first power. Remember we had 24 x1 squared, those were 2 1 cycles, and then x5 squared, those were, you know, 2 5 cycles from the icosahedron. And what's going on with this? So again, we replaced x1 with the sum of the first powers, and then x5 with the sum of the fifth powers. We replaced x2 with the sum of the second powers, etc. Okay. So, and then we of course divided by 60 at the end. Okay. This is a cycle index polynomial. So here is the moment of truth. Here we go. We're about to expand this thing. Okay. There it is. That looks to be the right thing. 1/60th times that mess right there. There's our cycle index polynomial with the variables replaced by these color things. And here we go. I'm going to show some more terms here. Okay. Hey, I want some more terms. More terms, please. More terms. There's 1,820 terms, by the way, in this, apparently. Okay. Look, there's a little dot, dot, dot right here in the middle. Okay. So let's see, show more terms. Okay, I'm not going to make it show all that. Well, yeah, I don't know. Maybe I will make it show all that. I'll see how far this thing will go. Okay. I like to push it. I like to push this thing to the limit here. So let's show a few more terms. Okay, maybe show a few more terms. And then we'll talk about this thing. All right. So what this thing is saying, so I have this giant polynomial expansion. What this thing is saying is I say, okay, well, how many of these, how many of these colorings, so I have 5 colors, white, red, blue, green, and yellow. How many of these colorings, how many of these distinct colorings, distinct under, this floating object, how many of these distinct colorings have all vertices that are yellow? Well, the answer is given by this first, okay, it's not very interesting, but it's just this first term right here. There's a 1 sitting in front of that. It's the coefficient of that y to the 12th, right? So there's 1 with all 12 vertices being yellow. And you say, okay, well, how many of them have a single blue and 11 yellows? Well, there's 1. Right, that's given by that summand right there. There's 1 in there, okay? And you say, well, how many distinct colorings have 2 green and 10 yellows? The answer is 3. That's given by that thing right there. And then you might really get creative and say, I want to know how many have a single blue, 3 greens, and 8 yellows. And that's given by this summand right here. There are 33 of them. And you might say, I want to know how many have 2 blues, a green, a white, and 8 yellows. 2 blues, a green, and white, and 8 yellows. And that will be given by this summand right here. That is unbelievable, okay? I don't know what to tell you to try to convince you of something being more fantastic than that, okay? In this world at least. That is an amazing result. That you can actually list almost in complete automation by just expanding the cycle index polynomial, replacing it by the appropriate thing. You flat out get the total number of colorings of particular types. That is Polya's enumeration formula. That's what allowed him to be able to compute very complicated isomers of certain kinds of molecular combinations. Okay, so that is an amazing result. I hope you see that, and I hope that this little example right here kind of reveals some of that to you. We're going to be messing around with this a little bit more in the coming lectures, but this is our kind of penultimate result for the semester. So I hope you enjoyed it. All right, just so you know, last homework is due next Wednesday, and it's the sections 9.3 and 9.4 combined. I'm going to post that in Canvas very soon, but that's your last homework set. Okay, what a nice little result to end the semester on. Hope you enjoyed it. See you soon.